Okay, so welcome to another lecture in the series of engineering chemistry, and this is lecture 6. So for lecture 6, we want to discuss acids and bases. So we have some properties of acid that we need. Some properties of acid, we have acid produces H plus or H3O plus in water, and H3O plus is known as hydronium ion, and this is an hydrogen ion attached to a water molecule. So acid corrodes metal. They are electrolytes. They react with bases to form salt and water, and they have pH less than 7. So when you dip blue litmus paper into acid, it's going to turn to red. They have sour taste, and and they also react with metal to produce hydrogen gas, and they also react with carbonates and bicarbonates to produce carbon dioxide gas. So some examples of acid, we have acetic acid, citric acid, lactic acid, ascorbic acid. So where we can find them are also written there. Then we also have some laboratory acids, your sulfuric acid, hydrochloric acid, nitric acid, hypochlorous acid, and propanoic acid. So these are common examples of acids. So some properties of bases. Bases generally produces OH minus in water, and they are also known as electrolytes. They react with acid to form salt and water. Their pH is greater than 7, and when you dip red litmus paper, it's gonna give you it's gonna turn blue. They have a bitter taste, and they feel slippery or soapy when you put them between your fingers. So many soaps that we use contain bases actually. So these are common examples: sodium hydroxide, potassium hydroxide, barium hydroxide, magnesium hydroxide, and aluminum hydroxide. So we want to go into the definitions of acids and bases according to some principle. And the first one that we're going to look at is Arrhenius definition or classical definition. So Arrhenius definition says that an acid is a substance that contains hydrogen and dissociates in water to give hydronium ion. Then it says a base is a substance that contains hydroxy group or ion and dissociate in water to give OH minus. So let's take note of that. For Arrhenius definition, it says an acid will contain hydrogen, and when you dissociate them in water, they're going to give you H plus or H3O plus. And base contain hydroxy group, and when they dissociate in water, they're going to give you OH minus. So by the time you had the acid of Arrhenius and base of Arrhenius together, you can see that it can easily form water because you're adding hydrogen and a proton, you're adding protons and OH minus hydroxy ion together, they're going to give you water. That's what we call neutralization. So the examples, this is going to be an Arrhenius acid because it contains hydrogen, and when it dissociates in water, you can see that it's giving us hydronium ion. Then another example is methanoic acid. So you can see that it also contains hydrogen, and when it dissociates, you can see that it's giving us H3O plus. So that's a classical example of Arrhenius type of an acid. So for bases, Arrhenius says that the base will generate OH minus in aqueous solution. So for example, if you dissociate sodium hydroxide in solution, it's going to split into sodium ion and then give you hydroxy ion. And that is another classical example of Arrhenius bases. Arrhenius says that when it dissociates, it's going to give us this. So this is a classical example of Arrhenius bases. So Arrhenius theory says that for any strong acid, it's going to dissociate 100% in water. So when you put them, in water, they're going to dissociate completely, complete dissociation. So these are examples. You have your nitric acid, sulfuric acid, and the rest. So for strong bases as well, Arrhenius theory says that when they dissociate in water, it's going to ionize 100% in water. So example is sodium that we mentioned earlier, lithium hydroxide, sodium hydroxide, potassium hydroxide, and so on and so forth. So when this compound dissociates in water, they're going to dissociate 100% according to Arrhenius theory. So this is a graphical example. This is the acid. When the acid dissociates, it's going to see the negative and the positive. All of them will dissociate completely. But if it is a weak acid, then at equilibrium, you're still gonna see that you still have a larger percentage of the acid that has not been dissociated, but we have very little of them. So this is a classical example of a weak acid. When they don't dissociate completely, then we say they are weak acid. Now let's go to another definition. Lowry-Bronsted definition now. It said an acid is a proton donor. That is, any species that gives H+, it's an acid. So that means an acid must contain H in its formula. So for example, you can see nitric acid has H in its formula. So all Arrhenius acid are Lowry-Bronsted acid because the two of them are generally saying the same thing. Arrhenius is saying that when they dissociate in water, they're going to give you H+. And before you can give H+, you must have H in the formula. So for base, a base is a proton acceptor. That is any species that accept the H+. So a base must contain a lone pair of electron to bind to the H+. We discussed lone pair electron when we were discussing Lewis structure in lecture 2. So for example, you have in ammonia, which is an example, a typical example of a base, Lowry-Bronsted base. Okay, so Lowry-Bronsted base are not Arrhenius bases. Why? Because all Arrhenius bases contain Lowry-Bronsted base OH minus. The reason is that, for example, let's say ammonia. Ammonia does not contain OH, and Arrhenius says that for it to be classified as a base, you must have OH, you must be able to produce OH. And when you don't have OH, there's no way you can produce OH. So for Lowry-Bronsted perspective, an acid-base reaction is a proton transfer. That is, an acid donates the protons to water, and bases accept the proton from water. So this is an example. You have a model example. Acid react with base, then they form a conjugate acid and a conjugate base. We'll get to the conjugate later. And then from there, we can see. From this reaction, we can identify what is an acid and which of them is an acid, which of them is a base. For example, HCl is reacting with ammonia. So HCl is giving out hydrogen to ammonia to form ammonium ion. So we now have 4 hydrogen here. So that means HCl is a proton donor, and a proton donor, according to Lowry-Bronsted, is an acid. Then the proton acceptor, which is ammonia that accepts the proton, it's a base because according to Lowry-Bronsted theory, any substance that accepts the proton is a base. So that makes this the conjugate acid of the base, and this is also the conjugate base of this, because this Cl minus is coming from here, and the ammonium ion is also coming from here. So the difference between Arrhenius and Lowry-Bronsted theory is reaction does not have to occur in aqueous solution. So for Lowry-Bronsted, they don't have to be in aqueous solution, but Arrhenius is talking about the reaction in water. So bases do not have to be hydroxide. So for Arrhenius, it's saying that they have to be hydroxide, but for Lowry-Bronsted, it's saying no, they don't have to have OH in their formula. For example, is ammonia. Ammonia does not contain OH. So, but from here you can see that ammonia is acting as a base, because here water is donating hydrogen to it. So from this case, it's a base according to Lowry-Bronsted, because it's going to accept one hydrogen to become NH4 plus, and this OH is being liberated from the water. So Lowry-Bronsted theory says there is always an acid-base conjugate pairs. So weak acid have strong conjugates, and weak bases have strong conjugates, and these are the reason why they are called weak acid or weak base. So if they have strong conjugates recombine to form the original species, and that is why they are weak base, because if they produce a strong conjugate, that means that the strong conjugate is going to recombine and then go back to the original product. And that is why they are weak, because if they are weak, if they are strong acids or bases, they are supposed to dissociate completely. But if they don't dissociate completely, they go back to the original, then they are weak acid or weak bases. So we've talked about this example. So you can see that ammonium ion must be the strong acid. That's why it's going to give up the hydrogen again, then it's going to go back. That's why we have a reversible reaction. So it's going to go back to ammonia. So it's going to give up the hydrogen, then perhaps give it back to OH to form water. Then it's going to go back to ammonia. That's why this is going to be a weak base. A weak base. Okay. So let's check this also. All right. This is going to be a weak acid. Otherwise, it's going to recombine with this to form NaOH again. And remember, NaOH is a strong base, and it should dissociate, ionizes 100%. There's nothing like going back. It should ionizes 100%, and that's why this is a weak acid. Otherwise, it will just recombine with OH and go back, and that's why we're not using a reversible reaction symbol here, because the reaction can only go forward. There's nothing like recombining, and that's why NaOH is a strong base, because it's not going to recombine. But this is a weak base because this can easily recombine. This is a strong acid, so it can easily give out the proton, then go back to ammonia. So we have some examples of acid-base conjugate pairs. So you can see nitric acid reacting with water to produce this. So for this is going to be the acid, because it's the one donating proton to water to form this. And the water is the one accepting the proton. So water is going to be the base. So that's why we have nitric acid is the base, acid, beg your pardon, and then water is the base. So so NO3 minus is going to be the conjugate base for nitric acid, and the hydronium ion is going to be the acid for the water. So as you can see, also HF is reacting with water. HF is going to be the acid, because it's the one donating proton to water, and water is the acceptor, so water is the base. So this is going to be the conjugate base of the acid, and this is going to be the conjugate acid of the base. More examples. So when you have acid and base reacting together, then you're going to have this kind of movement where you have acid and the conjugate base, the base and the conjugate acid. So for example, if this is the acid gives out hydrogen. So that means the A is going to be the conjugate base. The water is the base because it's the one accepting the proton. So it's the base, and then the product that comes from it is going to be the conjugate acid. So let's do some learning check. Let's identify the acid-base pairs for this reaction. So for the first reaction, HF is going to be the acid. Water is going to be the base. So F is going to be the conjugate base of HF, while hydronium ion is going to be the conjugate acid of water. So the second example, you can see that this is a methanoic acid. Is going to be the acid because it's the one donating proton to cyanide ion and then to form. So this is going to be the acid, and this is going to be the conjugate base, and this is going to be the base because it's a proton acceptor, and then this is going to be the conjugate acid. The same thing happens here. You can see that the ammonium here is the one losing one hydrogen to form this, and then we have the carbonate is the one gaining the hydrogen to form that. So you can see how these things have been related to one another. Protic acid. So we have different types of acid. We have monoprotic, diprotic, we have triprotic and polyprotic. So monoprotic, as the name sounds, it's the one that ionizes to give one hydrogen. So for example, hydrogen chloride is going to give one hydrogen, and that's why it is monoprotic. Diprotic, you can see they have two ionizable hydrogen. So for example, sulfuric acid is going to give the two hydrogen that it has when being dissociated in water. Triprotic means that they have three ionizable hydrogens. So example, we have H3PO4. This compound can lose all the three hydrogen present, and that's why it's called triprotic. So polyprotic means that they have more than one ionizable hydrogen. So if you have any acid that can lose 4 or 5, then they are generally polyprotic acid. So for base also it's the same. So we have monobasic, the one that can give OH group, just one OH group. We have dibasic, the one that can give two. As you can see, the barium oxide is going to give two OH minus. So we have acid dissociation constant. So when you dissolve acid in water, what is going to be the dissociation constant? So this is how we write the dissociation constant. The product in square bracket, that square bracket means the concentration, over the reactant, also in square brackets. So you write each reactant in square bracket and each product in square bracket. So those square bracket is meaning that it's we are talking about concentration. Okay, so for this case, mostly we ignore the water. When water is included and it's a pure liquid, then we ignore it. So we only have Ha as the denominator. So since the concentration of water is high and does not change significantly during the reaction, so the value is absorbed into the constant, and that's why we have the products, then we ignore the water on that. So the stronger the acid, the higher this at equilibrium. So if you have a very strong acid, it's going to give you a lot of hydronium ion at the equilibrium, and that means that it's going to have a large Ka value. Ka value, that's dissociation constant value. So we have some other things that here. So for a weak acid, you're going to have relatively high Ka, it's going to be relatively high. So for a weak acid with a moderate Ka, so it's going to be around 10 raised to the power minus 5. And for a weak acid with relatively low, then it's going to be minus 10. So, but for strong acid, we say they have large or larger Ka value. So you can see the table for Ka value here. So if you have any calculations, you can just consult the table of the Ka value, then you can look at the Ka value and use the Ka value for the calculation. So we also have for polyprotic acids. And we have several polyprotic acid, more examples of polyprotic acid. So for base, the dissociation constant is more or less the same as acid. Also, we also call it Kc, but for base we just call it Ka, where you have the product in square bracket, each product in square brackets, and then the reactant in square bracket. And again, you're gonna ignore the water for this value, so you're gonna have only this. You ignore the water. Then we have pH scale. So pH scale is a way of expressing the strength of acid or base. So instead of using the very small number, we just use the negative power of -10 in the molarity of the H plus or H minus. So pH is minus log of the concentration of hydrogen ion or the hydronium ion. So in the case of base, we can also use POH equals the minus log of OH minus the concentration of OH minus. So in that case, so since this is equals to this, then we say 1 times 10 raised to the power minus 7 molarity. So thus pH plus POH equals 14. So for the pH scale, you can see that the pH will from, you can see the red part is the acid, the acidic part, and the blue part is the basic part. So when you have a substance or with a pH of around 2, 3, you know this they are acids. But when you have substance of around pH of 14, then you know that you're talking about the base, because this is POH. We're talking about the base. That's going to be very high in terms of the concentration of OH. And then when it is 7, then we say they are neutral. Then you can see examples of compounds with such pH on the pH scale. So, but we can do some calculations. So if you have the concentration, then they ask you to calculate the pH, and you can just use the formula pH equals minus log of, for this case, we don't have pH, but we have POH. So we're going to calculate for pH first. So minus log of the concentration given to us is going to be 3. So if you punch your calculator, minus log of this to give you 3. So, but we know that pH plus POH equals 14. So that's why we're going to say, okay, now that we know pH, then we can say 14 minus 3, then we get the pH to be 11. So again, we can also calculate this. We are given the concentration of this. So it's just a matter of putting the concentration, then you punch the calculator, then you get the value for the pH. So for learning check, we can try that out. So also learning check, so go back to the notes and you should be able to answer some of this. So more examples on pH. So when you have problems like this to solve, so you are given the concentration of hydrogen bromide, then you are asked to calculate the pH. So this is going to be the concentration of the H plus, because for it to be an acid, then we are talking about the hydrogen. So that's why the concentration is going to be this. So you put the concentration into the formula for pH, then you're gonna get that. So try and do the same thing for the second learning check. This is going to be the concentration for what? For OH. So we are asked to calculate the OH, and this is straightforward. So we talk about the equilibrium. Equilibrium is a state in which there are no observable changes as time goes on. So you start the reaction, and then at the point you discover that there's nothing happening anymore. So that's equilibrium state. So equilibrium is achieved when the rates of the forward and the reaction are equal. So the concentration of the reactant and the products remain constant. They're not changing anymore. So we have this kind of reaction. So we're going to have a forward reaction and then a backward reaction. So at equilibrium, the rates are equal. So no further net changes occur in the partial pressure of the reactant or the product. So the rate of the forward reaction is equal to the rate of the reverse reaction. So according to law of mass action, the reaction rate, as if the forward rate, is the multiplication of the concentration of A and B, and then you have a constant being introduced. So, and then you have the concentration of reactant A, the concentration of reactant B, and then this is going to be the rate constant for the forward reaction. So we do the same thing for the reverse reaction, that's from the product backward. So the product is C and D. So the product concentration of product A, C is a concentration product of B, and the Kr is going to be the rate constant for the reverse reaction. So in definition proper, law of mass action says that for a reversible reaction at equilibrium, the constant temperature, a certain ratio of reactant and product concentration has a constant value K, and that is the K that we're talking about. So a number is equal to the ratio of the equilibrium concentration of products to the equilibrium concentration of reactant, each raised to the power of stoichiometric coefficient. And then let's see how to write the law of mass action. So you have your product, your reactant, and then the product. So the product is going to be the concentration of C and D, then over a concentration of A and B, that is the reactant. And then any coefficient that is there, you raise the concentration to power of that coefficient. So sometimes you can have for gases. With these gases, then you'll be talking about pressure. So Kc is a value that is temperature dependent. So Kc is independent of initial concentration. So there are some things we need to know about Kc. So the magnitude of Kc will tell if the equilibrium reach favors the reactant or the product. So for example, if Kc is greater than 1, that means the equilibrium favors the product. So if Kc is less than 1, that means that the equilibrium favors the reactant. So for homogeneous equilibrium applies to reactions in which all reacting species are in the same phase. And what do we mean by the same phase? That all of them are in gaseous state or solid or liquid state. So that's homogeneous. For example, this reaction is in gaseous state. G, the G gas stands for gas. So if you want to write the Kc, you write for the product, the concentration of the product raised to power the coefficient 2, and then the concentration of the reactant. So let's see how to write some expressions. Okay, the first equation, the Kc is going to be the concentration of this and this. There's no coefficient, so you're going to leave them like that. Then over the concentration of HF, and then the concentration of water. Remember what I said earlier, that for this kind of reaction expression, we're going to ignore water. So that's why we're going to take water out. And water can just be 1, and 1 times, so that's the final. So for this also, it's going to be the concentration of the product raised to power 2, yes. Then the concentration of NO raised to power 2, then the concentration of O2. So that's going to be the Kc. So the same thing we're going to do to this. Then for this, we're going to ignore water, like I said in the previous one. So we can now do some calculations, because it's possible that they're going to give concentrations of, remember I said that this square bracket means concentration. So if you are given the concentration, you just have to plug in the concentration into the Kc expression that you've written. Then from there you can get your Kc. So that's why the concentration of the product, you have 0.14. Then the concentration of the reactant, you have 0.012 multiplied by 0.054. So from there you can get your Kc equals 216. So we have also heterogeneous equilibrium. So results from a reversible reaction involving reactant and product that are in different phases. So the phases can be in liquid, gases, and solid. So for expressing this kind of the heterogeneous equilibrium, we have to omit pure liquids and solids. Keep that in mind. We have to omit anything that is, if it is liquid or solid, pure liquids and solid, we omit them in the equilibrium expression. So for example, you can see calcium carbonate, solid, is giving us CO and CO2. So that means, according to what we said in previous slide, we're going to omit solid, solid, so we only have gas left. And that is why Kc is expressed as CO2 for this kind of reaction. So your Kc is going to be CO2. So we're going to leave out the solid and the pure liquids out. So let me check. So let's see, let's try and write the Kc expression for the following. And again, we can also predict the direction of a reaction from Kc. So for example, we are given this, and from it they said that the Kc is 53.4. So let's write the expression for Kc first. So the expression for Kc is going to be that the product raised to power 2, and then the reactant, and then the reactant. So we were given the concentration. So by the time you plug in the concentration into this, and then you get your Kc. So this is what we are given in the question as the Kc. But when we calculate, we see that this Kc. So what does this mean? What does this mean? We'll see now. So we have something we call reaction coefficient. So this is done by calculating this, substituting the initial concentration of the reactant and the product into the equilibrium constant. So that is what we've done. So we've substituted the concentration into the equilibrium constant expression, and then we have 111, which is greater than the 53.4 that was given in the question. And what does that mean? So that means that the 111 that we got is Kc. So if Kc is greater, if QC is greater than Kc, that means the system will proceed from right to left to reach the equilibrium. So that means that from the previous example that we did just now, the QC is greater than Kc. That means the equilibrium is going to proceed from right to the left to reach the equilibrium. So that's going to be the direction of the reaction. But if QC and Kc are equal, then that means the reaction is at equilibrium. And if QC is less than Kc, that means the system will produce from left to right. So from the example that we did now, we can see that the reaction is going to proceed from, because this is going to be the QC now, which is greater. So it's going to proceed from right to left. So it's going to proceed from right to left. And that's QC, reaction coefficient. So when it is, this is another way of explaining it. So when it is less than Kc, it's going to move from reactant to product. When they are equal, then it's equilibrium. So when QC is greater than Kc, then it's going to move from product to reactant. So let's do more examples. We're also given the Kc of this to be 1.2. So let's see. So you said predict which way the net charge will proceed. So we are also given the concentrations. So let's calculate the concentration first, because the concentration is in mole. So we have to convert it to mole per dm cube. So all you need to do is to divide it by the liter, by the liter. So by the time you get the concentration of each of the reactant and the products, then you can now slot in into the QC expression. So by the time you slot in, and then you get your final answer. The final answer is 0.61. Then you can see that the QC is less than the value of Kc that was given in the question. and that shows that the equilibrium is the equation is not at equilibrium, and the net result will be an increase in concentration of ammonia and a decrease in concentration of N2 and H2. That is, the net reaction will proceed from left to right until the equilibrium is reached. It's going to proceed. You remember, they're trying to produce ammonia by combining nitrogen and oxygen together. So the Kc is far greater than Qc. That means the reaction will now move from the reactant to the products. You go and check the relationship between Qc and Kc, then you'll be able to understand clearly why the reaction is moving from left to right. For this example, and another learning check, let's see how we're gonna solve this kind of example, because this is a little bit technical than what we've been doing before. For this example, we can see that we were given the initial concentration of hydrogen and initial concentration of iodine, and then the initial concentration of the product is going to be 0 because there's nothing. The reaction is just starting, so there's nothing like initial concentration. So that means that we can say, okay, what is the change after the reaction has started? So we can say this is X, this is X. So if this is X and this is X, then this is going to be plus 2X because of the 2 that is here. That's why we say plus 2X. And this is minus X because these are reactants. Reactant, you are using up your reactants, and that's why they are minus. So for your reactant, we say minus, minus. Then for the product is going to be positive. So it is plus 2 because of the 2 here. There's nothing here and there's nothing there, it's just 1. So at equilibrium, how do you know the concentration at the equilibrium? That means you need to subtract the initial minus the change. It's going to give you the concentration at equilibrium. You do the same thing also for here. Then you do the same thing also from here. Then you get this. So now you can now put this concentration into the Kc value that we have. So by the time you do that, then you have a lot of maths to do here. Remember that we were given the Kc value. So from the Kc value, we can put the Kc value there, and then from there we solve for X. So when you solve for X, you get your X, then you can now go back to the equation and put X there. So for concentration at equilibrium of hydrogen, it can be this 0.5 minus the X that we solved for, 0.393, which will give you that. The same thing for this, and then the same thing for HI. So we have factors that affect chemical equilibrium, and these factors are concentration, pressure, volume, and temperature. So Chatelier Principle says that a change in any of these factors determining an equilibrium causes the system to adjust by shifting in a direction that reduces or counteracts the effect of the change so that the new equilibrium position is reached. We're going to use as an example to understand what Chatelier is saying here. So for concentration, when you increase the products, the reaction is going to shift, the equilibrium is going to shift to the left, that is the reactant side. But when you decrease the product, it's going to shift to the right side. So when you increase the reactant, it's going to shift to the right. And when you decrease the reactant, it's going to shift to the left. So you have to understand this very well and see the kind of effect that these changes can occur and when it comes to concentration. So you increase the product, then you know that it's going to go back to the left. So you decrease the product, you know that it's going to go back, it's going to come to the right. So the same thing, if you increase the reactant, then you know that it's going to go to the left, it's going to go to the right. And when you decrease the reactant, then it's going to come to the left. That's for concentration. For volume, so if you increase for volume and pressure, we're going to combine them together. So if you increase in pressure, means that side with fewest moles. So if you decrease the pressure, it's going to favor the side with most moles. So if you increase the volume also, the side with most moles will be favored. And if you decrease the volume, the side with fewer moles will be favored. So when it comes to temperature, we have two types. We have endothermic and we have exothermic. The endothermic reaction and the temperature decreases favor the exothermic reaction. So when you increase the temperature, you can see that the K will decrease for endothermic reaction and K will increase for exothermic. And then the reverse, when you do decrease temperature, you can see that K increases for endothermic reaction and K decreases for exothermic reaction. So let's see what we're actually saying here. So if a forward reaction is exothermic, if it is producing heat, that's why it's called exothermic, then the reverse reaction must be an endothermic. So the reverse reaction, so if the forward is exothermic, then the reverse reaction must be endothermic, and endothermic is when heat is being absorbed. So the change in temperature now. So for endothermic reaction, which is you absorb heat, when you raise the temperature, then the equilibrium will shift to the right. But if you lower the temperature, the equilibrium will shift to the left. So for exothermic reaction, if you raise the temperature, the equilibrium will shift to the left. But if you lower the temperature, the equilibrium will shift to the right. That is going to favor the product. Then catalyst. The catalyst will lower the activation energy barrier for a reaction. So catalysts generally speed up the rate of reaction. So if you lower the catalyst, the activation energy for the forward and the backward reaction is equal. Therefore, catalyst will decrease the time taken to reach the equilibrium. A catalyst does not affect the composition of the equilibrium. So the last thing for this lecture is solubility product. So solubility product is like, first thing we need to do also is to write the expression of the solubility, the reaction that we have. And the constant for solubility product is what we call KSP. So let's consider this reaction. Remember what we said about solid, that when you're writing an expression for this constant, we're going to neglect the solid. So for here also, we're going to neglect the solid, and then we have just the product, and the product, this is going to raise to power 2, and the product. So that's why we have solubility product as KSP equals just the product, because we're going to neglect this. So an example is when you have this and then they give you the concentration. So you are given the concentration of CaF2. So if the concentration of if the calcium ion concentration has been found to be 2.3 times 10 raised to power minus 4 mole per liter, then we should calculate the KSP. So that means as equilibrium, Ca2 minus is this. Therefore, remember that the two of them are going to have the same concentration, but because of the coefficient, you're going to multiply the concentration of this by 2 to give you this. Okay, so that after that, you can now multiply the two of them together to give you your KSP. So this is another example. We are given this formula, and the first thing is to write the KSP expression. Remember to omit the solid. So if you have to calculate the KSP, you already have the barium 2 plus, you have the concentration to be 3.6 times 10 to the minus 3. So then that means that for concentration of F minus, you're going to multiply this by 2. And then from there, you should be able to get the answer for the KSP. And that is the end to lecture 6. Thank you.